May I request President Indian Geotechnical Society, Professor IIT Roorkee, Professor N.K. Samadhya, and Honorary Secretary IGS, Professor IIT Delhi, Professor J.P. Sahu to chair and co-chair the second session, 8th IGS Ferroco Terzaghi Oration 2022. I request you to grace the dais, sir. Whose is this? Whose is this?
A very good afternoon to all of you. So we are meeting here again for the second lecture today, that is the 8th IGS Ferroco Terzaghi Oration, which will be given by Professor K.S. Rao, who is Emeritus Professor at Department of Civil Engineering, IIT Delhi. Will introduce the speaker. Okay. So, as you know, most of the information has already been given by Professor Babu and Professor Sahu regarding the IGS Ferroco Terzaghi Oration. So, this is the 7th and 8th in series. Actually, this was supposed to be delivered in 2020. But because of the pandemic, it could not be held. So this time we requested IIT Bombay and especially IGS Mumbai chapter to club these two lectures, these two orations, and they happily agreed for this. So I'm thankful to the IGS Mumbai chapter and also especially IIT Bombay. Professor Dasaka Murthy, Professor Juneja, and all the team, especially the students. So thank you so much for arranging this oration. So I think Professor Vishwanathan, so I would request Professor Vishwanathan to introduce today's speaker.
Good evening, one and all. I have been given the pleasant duty of to introduce Professor K. Seshagiri Rao, popularly known as K.S. Rao. And currently, Professor K.S. Rao is an emeritus professor in the Department of Civil Engineering at IIT Delhi. And he received his MTech from IIT Kanpur and a PhD from IIT Delhi. And he, I think, started his career in 1986 from IIT Delhi and worked for about 42 years, or I can say that working, because guided 26 PhDs, currently guiding 12 doctoral students, okay, and 190 MTech students. And he actually, I knew him since I think 92 onwards. we used to always meet at the parking lot in the next to the 4th block in IIT Delhi, very close to Civil Engineering Department. And we also have a close association in 1994. While I was the PhD student for some time in IIT Delhi, I closely worked with the IIT Delhi faculty for the international conference, the 13th International Conference on Soil Mechanics, and I think at the time it was called as Foundation Engineering. And at the time I happened to work with Professor Gulati, Professor G.V. Rao, Professor K.S. Rao, and afterwards I used to see him, Professor K.S. Rao, always in the IGS body only. And I also worked in Delhi. At that time also he was very active with the IGS activities. Even recently also we interacted for one of the committees for identifying in a committee for the best teacher award and all. So I could see that with his experience and all, he has given a lot of inputs to the committee. The another uniqueness is that he was involved in number of very difficult setups, like large scale polyaxial facility and static and cyclic direct shear apparatus, impact and creep testing for the rocks and all. The another I've seen also a couple of lectures, and I think his terrain of movement varies from maybe I think 0 to 50 meters, 100 meters. Sometimes he used to go into the hillock or mountain or whatever it is, for doing field testing. Sometimes it was really, we used to feel, very risky. And Professor Rao is an honorary fellow of the Indian Geotechnical Society and contributed, as I told you, more than 25 years in various capacities. And he also delivered IGS, 41st IGS annual lecture, and received the Kuckelman, very renowned and famous Kuckelman Award in the year 2020. And he actually has contributed particularly or contributing now in the area of consultancy in the form of a rock, earthquake geotechnical engineering, and recent works which include very difficult terrain in Jammu, Baromilla rail link project of national importance, and is also consultant for number of organizations like Delhi Metro, Pirpanjal, Rohtang Pass, Nasri, Chennai Pass. So you can see that Jozilla, sometimes we go for sightseeing, but he went for he goes for a technical recreation. So it was our pleasure that this particular lecture he has agreed, and he is delivering here. And on behalf of IIT Bombay as well as Department of Civil Engineering, on behalf of the organizers, I place a special invitation to Professor K.S. Rao, and I hand over the podium to the Honorable President Professor Samadia and the Secretary Professor J.T. Sahu. Thank you very much.
So now I request Professor J.T. Sahu to read the citation. Before that, I invite Professor K.S. Rao on the dais.
It's my pleasure to read the citation of Professor K.S. Rao, who is my colleague at IIT Delhi. Dr. K.S. Rao received his MTech from IIT Kanpur and PhD from IIT Delhi and joined the faculty of Civil Engineering IIT Delhi in 1986. He is presently Emeritus Professor in the Department of Civil Engineering, IIT Delhi. His academic and research interests span over 42 years. He has been, his research interest has been on engineering behavior of rock mass, stability of slopes, underground structures, foundations, etc. and new seismic hazard microzonation of megacities and so on. He is an established teacher, researcher, and active consultant. Professor Rao has supervised 26 PhD and is currently guiding 12 doctoral students. He has also supervised 190 MTech theses. He is the recipient of IGS Professor Lennart's Best PhD Thesis Award, Diamond Jubilee Award, Research Excellence Award, SC Verma Innovation Award, and 20 other IGS and ISR MTT Best Research Awards. He is a prolific writer and has published 375 technical papers in national and international journals and conferences. He has been the principal investigator of 13 sponsored research projects. Professor Rao has designed and developed several experimental facilities, which include a large-scale polyaxial test facility, static and cyclic direct shear apparatus for rock joints, prolifometer for 3D joint mapping, creep testing, high temperature rock chamber, rainfall impact analyzer, etc. A large-scale direct shear test facility for the characterization of mine dump material was established at CMPDI, Ranchi, under his technical guidance. Professor Rao is an honorary fellow of IGS and has contributed extensively to IGS in various capacities for more than 25 years. He was the editor of Indian Geotechnical Journal and IGS News. He has delivered 41st IGS Annual Lecture and received Kuckelman Award in the year 2020. He was the president of IGS for the term 2011-12 and the president of Indian Society of Engineering Geology for the term 2018-19. He was awarded the Lifetime Achievement Award in 2016. Professor Rao has provided solutions to more than 350 consultancies in the areas of soil, rock, earthquake, and earthquake geotechnical engineering. His recent geotechnical modeling work for assessing the stability of Chenab Bridge abutments has cleared the way for the construction of Jammu-Baramulla rail project of national importance. He is consultant to several organizations. He is extensively consulted for underground structure, hydel project, cut and natural stability of slopes, etc. In recognition of his outstanding contribution in the field of geotechnical engineering, Indian Geotechnical Society is honored in inviting Professor K.S. Rao to deliver IGS Ferroco Terzaghi Oration 2022. Thank you.
Okay. Should I get it there? Did you get it? Is it? That is there? Yeah, that is there. Yes. Yeah.
So, thank you, Professor Samadhya, President of IGS, so Professor Sahu, Secretary of IGS, Professor Bird, so for the excellent lecture, so which you have delivered. I don't know whether I will be able to match with you or not, ladies and gentlemen, so it's my honor to deliver the 8th IGS Ferroco Terzaghi Oration today. So the topic is the art of tunneling in challenging Himalayan ground conditions. It is the contrastingly different than what say the 40 years of experience Professor Boy delivered so just now. So let me clarify, like say the why I put that so the art of tunneling. So now it is a science or the technology. So if you see that the art means say something intuitive, imprecise, a skill cultivated through the practice and imagination of human brain. That is of course engaged in that activity. Science means something we know, researched, measured, and very objective. Obviously, both are poles apart. Coincidentally, interesting of the two, so you can make a perfect blend. The art means the things that we are doing in the conjunction with science of tunnels are constructed safely. So this is of course the one of the pioneer in the rock mechanics, and also the Professor Hook. The contrast between the any other structures and the tunnels are entirely different. So the tunnels are not be tested unlike any other structures. So they are different in terms of the construction material, loads, and safety requirements. Any other structure, so the normally we will be able to verify and do the test its performance, but the tunnels are not actually have that luxury of say the being tested. Tunneling is not a discrete science, so with different answers, many unknowns, and the answer to most of the questions, the answer it depends. The tunneling makes use of high technology, so equipment, advanced theory, but it is ultimately performed by human beings. So thereby, my calling it art of tunneling is fairly in place. I have very ambitious objectives, say that today. I don't know whether I will be able to deliver it, say that within this 1 hour. But yeah, I try to do it. So these are the contents, so which I will be addressing it to begin with. So the lecture is being classified into two things, part 1, part 2. So the part 1 is the fundamentals of design of tunnels, because the tunneling is not a usual subject that is being taught say in the engineering, unless you are maybe graduating it in rock mechanics, rock engineering, or underground structures, etc. So maybe 1 or 2 electives, so they could be there, so in the normal engineering program. So thereby there is always, so the necessity of just giving, some brief about the tunneling. So that is what actually I will be covering it in the first part. And the second thing is, so I will be the challenging in challenging ground conditions. So basically, it's a case histories, and large number of case histories I picked up here. I do have, so the 40 years of exposure to the academics, research, and as well, also the professional activity. So thereby, especially if you see it, say in the tunneling arena, so there are several processes by which the tunnels fail. So maybe under the squeezing, I do have some tunnels, and rock bursting, water ingress, so the cavity formation, so overbreak, asymmetrical loading, swelling, and ground settlement and phase loss. So the portal instability and impact and blast loads on shallow tunnels. This is the prime area in which say we have been doing the research. So thereby, not only the general information available, and so the specific research that is being done, so that IIT Delhi by our group. So I will be indicating it, say some of the findings, So also the seismic loads. So the normal impression is underground structures will not get affected by the seismic loads, but we have contrary opinions on that. So conclusions. So let's see, like, so the tunnel design and support systems. So the tunnels, underground passages basically. So for the highways, railways, sewage, water supply, public utilities and canals. They do have, so the several variety of shapes and sizes. So if you see this particular tunnel, so this is a famous Rohtang tunnel, and it has a 3D view of it, and the main tunnel, main chamber, so the up and down, so the two ways, and then you do have the ventilation, and our role is only making the tunnel. So but then, so there are several other requirements, so that you do have for the complete functionality of the tunnels, but that should be taken care, so in the design. So apart from that, so you do have, so the egress tunnels. So by chance, so if you do have the accidents, so you need to rescue, and the rescue can be done, so through the that, and then finally you do have the bottommost is the drainage. So tunnels normally, so they divide in two parts. So both sides of the drainage will be provided. So the section looks something like that. So the collected drainage, so the throughout, so that can be channelized and put it, so into the main drain. And the tunnels do have, so the different sizes. So the cross sections differs, so the depending upon whether it's a single or, so the double. So if you just briefly see the history of the tunneling, so is a prehistoric, so almost like, so the 2180 to 2160 BC. So some references are there, so the tunnels being made. caves connecting caves, so that becomes automatically the tunnels. So the largest tunnel 36 BC, so it's very remarkable, so the 1600 meters long and 8.3 meters wide and 10 meters height. It's a very big, so the in that sense. So of course 1681, so you do have the gunpowder. So then subsequently the excavation becomes, so the much more easier, and then the Seacon tunnel 1988, so they was the largest during that time, and some subsequently. So there are many tunnels across the world. If you see it, so they have been there for the different purposes, mainly for the railways, roadways, or the waterways. And in India also we do have, so the large number of tunnels that are coming. So as President said that, so the Jozilla Tunnel, Pir Panjal Tunnel, Chenani, Nasri, Rohtang, most of these tunnels are, so in the Himalayas. But across the country there are several tunnels which are actually coming for the railways. So some of them, so they have been there. The present scenario of India in the tunneling arena, something like this, so the 1641 tunnels spreading in 3445 kilometers. So they are in the different stages of construction. 77% will be completed and 23 will be under construction. A total of 280 tunnels of roughly 890, say that will be done, so the very soon by next year. So another, say the 117, so 137 tunnels, so they will be coming up by 2016. So the summary is, say the design, the tunnel design approach, methodology, and the challenges are different components, so the which will help in understanding the tunneling practices, so especially across the world, across the India. So as usual, so for any groundwork, if you want to do it, so you need to do the extensive investigations. So the ground conditions, so the groundwater plays a very significant role, and then the in situ stress state is also very important, say for the underground, say the structures. So this is the normal things which we do it, so the geological and geotechnical investigations, we'll be doing it, so the, and getting the design parameters. So these are some of the design parameters, so they have been listed there, and the corresponding tests which we will be doing it, so for the rocks and soil, so that is listed there. So we do, of course, so the extensive tests on soils and rocks, so in the laboratory to get the fundamental properties. Unlike the soil, so soil you can get undisturbed samples. So but the rocks, if it is fractured from the field, you won't be getting undisturbed samples. So that's the difference, major difference, and major lacuna in getting the field parameters of the rock mass. Rock mass is the one which is having intense, say the joints. So depending upon the different degree of jointing, we will be classifying the rock and also into different classes. So you have the investigations that are carried out, say pre-construction, during the construction, and also while the tunneling process is actually happening, so that we keep doing the investigations. So tunneling is the process by which, say by whatever you have excavated, so that you should, verify it, and then, say the make the plan, say for the next. The important in situ stress state in the earth is, say something like that. So this we know it, so as you go deeper into the depths, so the vertical stresses, so they increasing it. So with all these data available, so you will be able to know it, so what is the general the gradient of the stress. But most important thing is, say the in soils, so we take the K naught, say the 0.3, 0.4 or so, say for all our designs. But contrary, the rocks are different. So the rock terrain will be having it, so the horizontal stresses will be much larger than the vertical stresses. So thereby, the K naught values, so they will be almost, so they're going up to 1, 2, 3, 4, 5, 6. So in different, hilly regions. Being the Himalayas, the tunneling is actually happening we expect, so the very high horizontal stresses. So what is that, so that is going to do to us, so that when we are doing the tunneling. These two cases, if you see that, say the actual measured details from the Heidel projects, if you see that the mark these two, say the overburden is fairly, say the same 200, but if you see the sigma h, so the maximum principal stress, so that is it's very large, so in comparison, so with the. So it's not just, so the stress is actually being contributed, so by the overburden, but so the due to the tectonic reasons, so the at locations, so that you do have. What we do it, so yes, there are analytical solutions are there, classical. So you can get, so if you make the opening surrounding that, so you will be getting the radial as well as, so the tangential stresses, and then sorry. So apart from that, so these the in situ stresses which are get influenced, so by the by the shape as well as, see the direction of the stress state. So we know that, so the in situ stresses are the moment, say it is a stress, so it's having a direction, so they as well as, so the intensity. For example, so the let us see. So this is the inverted D shape, the tunnel. So then, say if the stress state is the sigma 1 is, so the greater than the horizontal stress, obviously, say the on the sides, so then in the tunnel walls you will be getting the deformations large or the collapses. So whereas if you have this type of stress state, so the crown and the invert will be having the issues. But if you have the direction is actually the inclined, so maybe the springing level or the crown part, and then, so the invert corner, so they will get. So by seeing the tunnel deformations, when they are excavated. So probably we'll be able to have, say the guess what is the stress state. Now let us see, like, so what you do it, so how do you do the tunneling process. So you mark the borehole locations. So then, so you charge it, you blast it, and then, so you evacuate, so the muck. So this is a cycle. So for all these 7 or 8 operations, so what is the amount of cycle time that is actually the taking. So that depends upon, so that decides, so the progress of the tunnel. So if you converge the cycle time, say smaller and smaller, so obviously the project will be completed, so quickly. So the open excavations, so then we know it, so that is the cut and cover. So we can have it, so the bottom up or the top down, so the processes which you can see it, so here. So up and down railway track is actually being done, so through the cut and cover. So normally this is the process, so by which we go. The simulation is actually goes like that. So thereby you will be having a tunnel that is actually the made, so that shallow depths. So we had, so about the TBMs, so the tunnel boring machines. So these are the giant machines. So they're having a roughly, so the length, so the 100 meters to 150 meters. So it's like a factory. So whatever the requirements are actually there for making the tunnel and stabilizing the tunnel. So every component of it is, so that goes along with that. So you do have a large cutter, and then if it happens to be the soil, so obviously the air pressure will be there. So the air pressure balancing, so the machine required. So thereby there is a separate chamber, so in which you do have the pressure managing system. So depending upon, so the site conditions, and then, so the cut material will be coming out, so through the screw conveyor. Whereas, so if it is a TBM, so the TBM you do have the cutter. So the cutter having it, so the wheels almost, so the 100, 110, so at different locations. So thereby in one go you will be getting a very clean the cutting. So what I want to say is, so the TBM machines are big machines, so they are having it, so the very large variations. Now come to the NATM. So the most of the time, so we keep talking about the NATM. So this is so when you do the tunneling, so you just, so they put a flexible nominal support, and then, say the complete the closure, so that, so the stress distribution, so they will be equally spread. So that gives the, so the stability to the tunnel, and then after that, so you will be doing the rest of the other observations, especially the monitoring is essential. So that is the reason why we say that NATM, as you see means, so the as you so the do the measurement, whatever you are getting it, so based on that, so the you keep changing the your strategies. So this is how actually it is being done. So the holes, then the charge, then, say the excavation, so then lattice girders, so they are put in because the strata is, so they're very yielding the conditions. So then after that, so you put the membrane, and then you do the RCC, say the final lining. So the final lining is the one which is actually going to take the loads, and the primary lining is, so to initiate, so the progress of the tunneling process. So in case, so if you are doing the tunneling, say in a very poor rock conditions, so or the soil conditions, so what do? If you make the full section, so if you open the full section, so then collapses, so they will be there. So thereby it is heading and benching. So that is the process by which, so there will be. Means instead of actually the full face excavation, so you will be doing part by part, and secure that, so the water, the part that has been actually excavated, and then subsequently, so the other parts, so you do it. You see that, so the in one single go, if the good rock conditions are there, so you can do the drilling, you can do the excavation full, but so if you do have, so the very yielding type of ground, so you will be going part by part, so the first you go there for some length, and then, so you take the sideways, and then, so after that, so you remove that. So it is a very painful process, so it's a very slow process that is normally, so we do it. So the game of tunneling is managing the deformations. After all, so initially the rock is, so under the equilibrium conditions, but by doing, so the tunneling, you have disturbed it. So you need to find it out, so when I do this type of operations, so what type of deformations that I am going to induce into the system. So, and then also like, so how do you control it? That is all, so the tunneling about. So controlling the deformations. So if the deformations are actually the large, so then, so that don't do it, so that do it, so the part by part, so that you are safe. So this is a comparative, the statement of, so when you use the NATM, so in different rock conditions, so you are using the TBMs or soft rock or hard rock or NATM, so if you use it, so what is the advantage, disadvantages, so or where you should, so they use it a particular process, so that's given there. You see here, so the progress is, so the very minimal. So, but whereas, so if you are using the high-ended TBMs or EPBMs, you can go tunneling, so much faster. So, what type of supports, so normally we go. So, these are some of the supports, so the systems, so which we use it: steel arches, rock bolts, so shotcrete, wire mesh. So the 5 groups are the 4 poling, and then, so the concrete segments, so then we do it. So these are the different variety of bolts which are actually available for the very hard rocks and soft rocks and the yielding ground. So variety of bolting domain that is available, say for the industry. So apart from that, so when you do the excavation, so obviously, so the stresses will be redistributed, and so you will be getting an elastic zone, and the immediate plastic zone should be tied up. So that's how actually we do the bolting. If you have the occasional blocks are there, so the jointed rock, you will be doing the rock bolts, so in those locations, and then try to stabilize the immediate blocks of sliding. So once you do that, so the rest of the rock mass, so will be stable. Sometimes you do get, so your face itself is actually the collapsing. So the one which you wanted to excavate, that itself is actually going to fall. So thereby what you do is, so you will be glass fiber reinforced, so the polymer rods, so they will be inserted to begin with, and then after that, so you cut the tunnel. Similarly, like, so this is, so the pore bowling technology. So because the roof is collapsing it, in that, so you create a artificial canopy. So by inserting, so the 20 meters roughly the pipes through which, so you can do the grouting, and then, so they create a canopy, and then under that, so you will be doing the tunneling. And these are the yielding type of the support systems, so normally we call it the lattice girders. So if the rock is actually squeezing it, so you try to create, so the required flexibility in the support system. So thereby, we always say that, so that Terzaghi is the father of the soil mechanics, but I don't know, like, so how many of you know it. He has, so that done very vital contributions, so in rock mechanics, so as well. In 1946, so he has given this particular classification system. He has the rock mass conditions, so in 9 categories, so he has categorized, and then also given a theory, so how if because during that time, so the rock support systems, no bolts, nothing, no shotcrete, but only the steel ribs. So they used to get the support, so through the steel ribs. And then he has actually created a theory, so what is the total weight which is actually coming onto this steel support. So accordingly, so based on the different classes, so he has given how to calculate it. So it's a fantastic thing. That apart, so subsequently the whole rock mechanics is, so the classification systems are design methodologies. In soil, so we use, so the very limited purposes soil classification, but in the rock mechanics, say classification systems are the main, say the primary design methodologies. You can find it out, say what is the type of excavation you can, what type of missions you can do it, and what is the intensity of the support system that is actually required, that also you can do it. So the birth of the rock mass classifications, so they came from this, so the Terzaghi's, so classification. So most of you must be knowing it, so the RMR classification is a very important classification. So Benevsky, from the experiences of mining of, say the South Africa, he has selected, so the five influencing parameters with a directional adjustment subsequently, and so each one is having importance value. So that is expressed, so in terms of the rating, and then total rating is 100, and they have been categorized, so in these classes, class 1, 2, 3, 4, 5. So if I have a class 1, so obviously, so I am dealing with a good rock. I don't need, say any support. So this is linked with, say the stand-up time. Means unsupported span, how much time, so it is going to last. Is it going to last, so the 10 hours or 10 years, or, so the forever. So how do you get, forever scenario? So obviously, so if the rock conditions are very good, so the tunnel is not actually going to yield. But if you are dealing with, so the very poor rock conditions, so obviously you need to support it before you, say go, say far. Most of these, say the classifications, say they were originated, so in the era of drilling and blast type of excavation methodologies. But subsequently, say as you have seen, like we have the TBMs, and because of the TBMs, you do the less disturbance, so the of the tunnel. So there may some improvement of classification rating, so that you can do it. So that's what actually the subsequently RMR TBM. So if you have a basic RMR, and then so that you wanted to use it, so the for TBM excavation, so you can do that, so by that. Another classifications system, so they came into this similar time, 1974, by the Barton and colleagues. This is, I feel that, so the very more scientific, so the RQ by JN, this decides the block size. The JR by JA is going to give you the internal friction between the block, and then, say the amount of, so the in situ stress. These are the three things, so for any failure. You take a slope, so obviously, so what is the block size, so that, and then what is the frictional value along the sliding plane, and then, so what is the amount of water pressure that is actually going to be there. So I feel that, so that it is a very good, so the scientific way of, so the looking, classifying the rock. He has, of course, this is, so logarithmic scale, so the 0 to any value one can, but most of the from the good rock condition to the worst rock condition, you can be captured, so within that range. So this classification, so is linked with, say the another, so the ESR and the span length, so that ratio. So with this, the importance of the structure is actually coming into picture. So as well as, so the required support system. So this gives, so the carefully, if you see it, so you will be able to design, like from the geological data and the geotechnical data, you are going to get, so the Q value of the rock mass, And then subsequently, you can, so for a particular type of tunnel or excavation you are making it, what type of support systems, so you need it prior to the actual the doing the tunneling. After that, so how do you link, say these classification systems with the rock mass properties? Because rock mass properties are required for the design. Of course, so the armor and other classification systems, so they created the empirical domain. So through that, so you will be getting the parameters. But the GSA classification, so they came in very recently. So that is very simple. And if you have a basic knowledge, so of the rock structure and the intensity of, so the fracturing that has been actually taken place, so that is the decreasing surface, that is the surface conditions, and then so the structure. These two parameters you can actually assign so the sum number, and this number is actually the correlated so with the Hook and Brown so the generally accepted so the failure criteria. So if you have the intact so the properties, so based on that so if you know the rock classification number, so through that so you will be able to get the material properties. So the material properties will be used so for the design of so the proper design of tunnels. So proper design in the sense say for the numerical analysis as well as so for the analytical solutions so if they are available you can. So this is how actually we normally so they do it so the ground response analysis. Any ground so you need to have it say this particular template. So how the ground is actually going to behave, so the when the tunnel is actually excavated, so the boundaries will be having it, so the very high stresses will be there, and but at that time, so you won't be able to give the support system. So thereby to provide the support system, so it will take some time. By the time, so the yielding is actually going to take place. Some amount of so the deformation or the displacement of the boundary is so the definitely required. So thereby so this line is actually going to decide so the when to give the support so for a particular so the excavation. Of course so these are different aspects of so how the displacements and other aspects so they will be calculated. So apart from that so like when you are doing the tunnel, so there is a some sort of silo effect. So on the face so the loads are actually coming, and if this is the scenario, so you have the vertical loads are there, and so this is so the almost zero because you have excavated. So obviously this wedge is actually going to fail. So if the wedge is actually failing it, so you won't be able to go forward because your face is actually collapsing it. So you need to provide so in the opposite direction. So the support system, that is what actually that say the face support so we'll be doing it. Of course we do have so the variety of numerical the modeling methods are there, and so they will also so will be of use, great use rather. So how do you the tunnel if the tunnel is actually having it so or the groundwater is heavy, so you need to channelize it. So thereby the tunnels are actually divided into two categories. So you have the drained and undrained, and in the drained tunnels you allow the water that is actually the seeping, but so they capture it and then so they put it down in the drain. So that means so you should have a very effective membrane system, so which can actually collect it. So maybe the details of it so they are there. So apart from that so the monitoring is the real important so the thing. So thereby what I said is so as you see, you do the tunneling so as you see means as you monitor it, you keep monitoring it, and then you keep securing it whatever that has been, because the tunnels are actually going in the horizontal direction, cutting across so lengthwise, when you are going, so the lengthwise, your geological conditions, so they will be grossly changing it, so the location to location. So you cannot actually start with, so the a particular method, so by which, so you can do the complete, so the tunneling program. So it cannot be. So thereby you need to, so they do the monitoring, extensometers, the pressure cells, the stresses, etc. in the lining. And then also the surface settlements, so they, especially in the metro tunnels, you need it because the metro tunnels are very shallow. So that is also initiated. Entry points of the tunnel is, so the portals. So the portals are very important. So they are, so the typical slope stability issues, and variety of failure mechanisms will be there depending upon the joint conditions. And you have, so the toppling and, say the sliding, the wedge failures if two joints intersecting it. And what we have is, so the beautiful method that is available, kinematic analysis. So normally we talk as stereograph projections. So this method can actually the complete, so as you do the engineering, so you will be able to comprehend, so visualize very nicely what type of things are going to come across, say as you do that. Of course, so if it is a soil, so we have a typical slope stability methods. So maybe the typical Bishop's method that has been actually given there, and then you have the tension crack is there. So then you do have a sliding plane. So if you put a bolt, so obviously this wedge is actually going to be. So this type of the measures we need to do it, so for securing, so the tunnel portal. So this is the tunnel portal. So normally, so the tunneling is actually done in the mountains. So the mountain face, so you need to properly, stabilize it using the different variety of methods which have been shown there. So that is what actually my introduction, so for the tunneling. And pardon me, so I have taken, so the more time for this, but then, so now we will be doing some, so the challenging conditions, so that we will see it, so the so the 75% of India's hydropower is in the Himalayas, and these are the states in which, so they are the Himalayas are spreading, and lot of railways and roadways, metros, water supply tunnels, so they are coming up in this particular area. Himalayas are unique, and so almost like 8.8 kilometers, so the height Mount Everest, and tectonically active because these mountains, so they came in through the tectonics. So if you see the east to west, say the spread, it is a large. That is more than, so the 2,500 kilometers long. So that is the spread of the Himalayas. So can be divided into three. So you do have the Great Himalayas, so inner middle Himalayas and the sub Himalayas. So if you take a section, so something like this, it is a Indian subcontinent, so the colliding with the Eurasian plate, so thereby the subduction zone, so thereby the whole area is, so is having a lot of thrusts and highly fractured, so the material. So these are the different, say the major MCT, MBT, and many other, say the thrust zones are there. So thrust zones are, so the reverse faults when two blocks are actually collided. Obviously, say the one block is actually goes down, and the other one is actually riding over it. So thereby it is always a weak plane, and then that is one of the reasons, so the Himalayas produce very high magnitude, so the earthquakes. So they are different, so you have so much of, so the fractured zones are there, due to the presence of, so these MCT, MBT, and associated faults. So they are very potential for the sliding, anisotropic in content, because most of the rocks are actually the shales, phyllites, gneisses, and schists. So these are terribly anisotropic. So location to location, they will be keep changing it, and the section looks, so something like that. And yeah, now what are the challenges, so that we normally come across, so in the Himalayas. Maybe the portal sliding, so that is the slope stability issues, and then so the water bearing strata. Himalayas, so when the Himalayas are forming it, there are so many river channels, they got entrapped, so into the Himalayas. So thereby they are charged with water. So the moment you puncture it, unending amount of, so the water comes out. So thereby water ingress issues are there. So the cavity formation, swelling, so the ground settlements, the phase collapses. There are, of course, the limestones, so the sinkholes are also do create the problems. The spalling, squeezing, rock burst, and then so you do have the earthquakes as well as so the impact loads. These are some of the details about so the hydel projects which are done so in the Himalayas, and what type of so the problems you have come across. So over breaks, poor strata, squeezing, high over breaks, etc., etc. Even sometimes so you do have a lot of so the gases coming. A good example of the type of problems which are going to come so the subsequently. So this is squeezing, because when it was excavated, is fair, is good, so the rock is good enough, but then so with the time so it gradually so the crumbles down, so the material is actually the squeezing into the cavity, so thereby failures will be there. So the creeping, the shearing, and so the rock bursting, this is the worst condition. So generally so the highly brittle materials, very strong materials, so good for construction, but then say the three-dimensional stress state, so you are manipulating it, you are changing it without knowing it. So thereby in one direction, so if you remove it, so the tunneling direction, so you are making the stress, so the zero. So obviously the material is going to, so the subjected to this type of failure. It is supported already, the steel ribs and other things, so they're there, but they will be completely crashed. So sudden brittle material, and then sudden so the collapse. So these things so the are very important, and then this has been so the one of our research area so the presently as well. So by doing the initial investigations, so you will be able to comprehend what type of problems you may be getting into it, and then thereby you are so the prepared to yeah. So apart from that, of course, so the similar type of thing, and then let me take so the first case of it. So this is the Rohtang tunnel. It's a very famous tunnel. So the highest tunnel, say at 3,000 meters, both the north portal and the south portal at 3,000 plus, so the altitude. That the cross section looks say something like this. So the most of the formations are actually dipping in this. I will come this particular thing later. So there is a Serinala, I will come later. So please remember that I will be calling again that name. And if you see the approach, so the wow button is actually varying it. So that is the tunnel, so the north and south. But this is almost like so the 1.1 kilometers. So just imagine that so your train is actually passing below the 1.1 kilometers. So you can very well so the imagine that so the what is the type of the stresses which will be there. In some sections say they have issues, so that is the squeezing conditions. So the squeezing conditions can be handled say the empirically, semi-analytical, analytical, and then the numerical. So within that so again several attempts are actually there. What we did is so as the tunneling is actually the proceeding it say the huge amount of data that is coming out. So the phase mapping is done. So based on the phase mapping so you will be getting you can try to so predict it, of course, so the classification systems etc. will be keep revamping it as you do the tunneling, and then so to begin with you do the numerical studies. So from the numerical studies it is very clear, so some sections are having the issues, so the a plastic zone, one can actually predict it, and also the major principal stresses, and then so if you have that type of scenario, so that is the type of convergence which is actually taking place. To ward off that, so you put the bolting system. So that's what actually normally what we call is so the support system. So at IIT Delhi, we did a lot of say investigations on squeezing conditions. And then, so based on that, so the three variety of predictive models, so that have been proposed, and then they will be compared, so with the other. And then what are the solutions? The solutions are, so the yielding steel arches, so which will be there. So they will be get adjusted, so as the tunnel is actually getting, so they squeezed. Apart from that, so you have the lining stress controllers can be embedded in the lining, and these two methods, so the one can use it, so to control it. So both these systems are successfully deployed in the Rohtang tunnel. So the tunnel is commissioned and providing a great travel experience. So I will come back again to this particular tunnel subsequently. Now let me introduce so the great project that is actually happening it in India. So that is in J&K, connecting the plains, so to the Srinagar and beyond. USBRL, so that is the Udhampur Srinagar Baramulla rail project, 272 kilometers, and it is a mind-boggling terrain, starting from Jammu or Udhampur. So this is one segment. That is Udhampur to Katra, so the Katra to another segment, say that is the Benihal. So the Benihal to Kajigund to, say the Baramulla. Baramulla is, so the beyond Srinagar, and you are cutting across, so the highest mountain ranges, so the having altitudes of very high magnitude. See the amount of this one single project is, so they having in these four zones, so the handled by the IRCON and KRCL, Northern Railway, and lot of stations. So then I think maybe this is interesting. So the major bridges, so more than so the 900 bridges are actually coming, small and major bridges. The world's highest bridge, say the first and the second highest bridges are coming, so the in this place, in this particular, so the route. So I take, so the one single project, so for which I was technical advisor. So that is the Pir Panjal. So going, so virtually the south to north, and so the cutting across, so these mountains. These mountains are, so the all season. So you have the snow clad. So you cannot actually normal routes, so the closure for 6 months, and but now of course, so all weather tunnel project which is actually the coming, so they here. And in the center part of it is, say 1.1 plus, so the meters, so the kilometers height, and the portals are, so the is very shallow depths. So the rock formations are, say very variable, and so these are the two portals, and the equivalent cross section, so there is something like that, and then it is a single railway tunnel. So with other, so the provisions. So you have the primary lining, and then, so they do have the concrete, so the lining is actually there. So this is a railway tunnel. So we did the numerical modeling to at all the sections which are actually the vulnerable, and also like, so they using the FLAC also the similar analysis, so that has been attempted, and then it is very clear, like, so the out of the many sections, so the section where you do have the shale, of a particular chain is, so the having, so the issue. So how do you mitigate it? That's what actually the given here, the different stages of, so the mitigation, and then finally you will be able to complete the project. So as I discussed, so the earlier pore polling techniques, and then of course, so the shotcrete thicknesses are varied in this particular zone. So they, as well as, so the yielding and yeah, this is already the tunnel is made because there are so many tunnels, so in this particular USBRL project, so the more than 68 tunnels are there, so the small and big. And this is one tunnel which has been actually made, but then subsequently the shape is inverted, the D shape, and then so the steel lagging and other things, so they are done. So but the tunnel started actually the collapsing it. So why this particular tunnel, so they collapsed? So the shape is not really, so the is good for the this strata conditions. So thereby what we did is, so the reprofiling of, so the tunnel. So some sort of, so the top oval and connected, so the completed the bottom invert, and then this is the shape with, so the different, so the support systems which are actually mentioned there. So this gives you the final shape that has been actually done. So it is perfectly now, so the reprofiling of the tunnel T10 is completed. So and the tunnel is, so ready for the commissioning. So the commissioning was held because of, so the completion of the two iconic, so the bridges. So that is the China Bridge, which is having a height of, say 359 meters, say the higher than 35 meters higher than the Eiffel Tower. So the another Anjikat bridge, say this is another second largest bridge which is actually coming. These two bridges, when they are ready, so then, so they you will be. The other thing is, so the rock burst. I said that, so the highly brittle materials, so you will be sudden release of the stresses, so in a particular direction, so will be subjected to the rock burst. And rock burst can actually happen, so there are several ways. So I take one project, so under this, so that is a Parvati hydro project, power project. So the cross section is something like this. So where do you have, so the high strength Manikaran quadrates. So as you know it, so the quadrates are the highest, strongest, so the rock types. And you have the quadrate, and then the rest of the length of the tunnel is, so they having the phyllite schist, slates, gneisses, etc. Then in this, so in one segment that has the TBM has been actually engaged, and suddenly, say the rock burst occurred. So thereby the TBM stuck inside even now, and so that is still stuck, so thereby it is not yet complete, so I have not actually put my last, so the statement on that. So still it is going on. When the rock bursting is actually taking place, so the rock must be, so they're giving some signals. So what we call is, acoustic emissions. So acoustic emissions, so the technology is actually developing, because underground mines, as well as, say this type of, say the situations, if you monitor it properly, probably you will be able to get, say the prior to, so the real collapse, you will be able to stop it. So that is the attempt, so the which we have been doing it, so that IIT Delhi, and of course, so the results are not actually put it, so the in this. So the so what our anticipation is, so the findings would form a base to develop suitable analytical and numerical models to predict and prevent the rock burst, so in the future. So it's a major game changer. Several teams, so they are working it, say across the world, and we do. Water is everywhere, so in the Himalayan tunnels. So as I said that, when the Himalayas are formed, so the aquifers are actually got entrapped, so they are charged with water. So it's a mind-boggling, so the amount of water that comes, so from these, so the projects. The mitigation measures, so they have been listed, so there, and now let me take, this is Udhampur Katra. So there's the tunnel number is, so there is given there, so the T25, and so the pipe roofing and the surface grouting, that is the two methods which will work in this, and of course you will be draining it, so the water for some time, and then subsequently, so you start actually doing that particular mitigation measures. This is another project, so the tunnel T5. So the in this, so you do have the water logging. So the actual geological the section looks like that, so all the lines indicates that, so that you do have, so the lot of, so the joints. So drilling and blasting, so the method that has been actually utilized. Now you see the scene of workplace. So it's a treacherous, so the projects stuck, so for many months, so because the water is actually keep oozing it out. Finally, of course, so we could, so the T5 completed, so successfully completed there. This is very interesting. So Rohtang project is an iconic project. So Atal Tunnel, that is what actually we recast the name recently. So interior is the most sophisticated. So it is a 9 kilometers, so the road tunnel, and with all the modern facilities, and also the escape tunnel that has been, so there. But after 3 months, so what we found is, so the one particular section is getting, so the some sort of, so the seepage. So seepage indicates that, so the some amount of leakages are actually coming. Why that is actually happening it? So the ministry has actually formed a committee to look into this issue. So this is really what happened it. It's not that, so this problem is unknown. So even while the tunnel is actually being constructed, so we had, so lot of troubles, and then somehow, so the project is completed. Now you see that. So this is Bias river system, and say this is one Seri Nala. Seri Nala is actually having the 4 parts, and one Nala, the branch, say that is cutting, that is flowing down. That is the root of, say the Seri Nala coming from the higher regions, and then the Rohtang tunnel is actually going in this direction. So obviously there is a superimposition. So more than, say 1.5 kilometers means your tunnel is actually coming under the Nala. So thereby there is, say the 1.5 kilometers, so the charged with heavy water. So the in December months or, say in the winter month, this particular channel is, so the full of ice, so that it keep actually melting it, and then thereby charging the tunnel, so with the water. So I think, so the information is, so that you can read it, so the later as well, so through my note. And when we constructed this, so definitely we used a beautiful, so the membrane, so to trap the blue line is, so they indicates the membrane. So you have the primary lining, and then, so you have the final, RCC lining is there, and then in between, so you have the membrane is there. So this is the dimple membrane. So it is a designed membrane. So thereby any drop of water that is actually coming, so through this first, so the lining, so will be captured, and then that will be brought back, and put it, so in the drain. But if you see it, so what is the drain state, so it is only the awful. So that indicates that, so the membrane is actually got choked in that particular section. So thereby the water is actually penetrating through the construction joints of so the lining, like RCC lining, which is actually there. And for every 14 meters, so you do have the construction joints. So through these construction joints, because of the choking of membrane, the water is actually seeping into the walls, so thereby creating it, so the issues. So thereby, the government of India wanting, so why don't you change the course of the Nala? Great, so we have so many, so the hydrological engineers are there, so they did wonderful things, so for the hydro potential tapping. So why not, so they change the river course or the tributary course? That's what actually the duty given to our committee. Of course, Professor Mahendra Singh is also one of the members. And we went through all the possibilities and then finally recommended, so the construction joints will be sealed, so with the suitable, so chemical grout, so thereby improve the condition, so in the tunnel. So apart from that, so the reduction or the diversion of the water from the Sirinala. So that's 1.5 kilometers, so Sirinala segment. So that, so that you can, tap it, so through the pipelines and then put it, so the downstream. So thereby, the recharging of the tunnel section or under the that particular, so they will be minimized. So both these measures are recommended, so for the implementation, and works are actually under progress by the BRO. So BRO has actually given the work to the NHPC for the detailed BOQ, and then subsequently, so the work will be continuing. So this is the Jozilla Tunnel. So again, water problem. So since we have discussed, so the many water problems, so I will say that, this particular tunnel is construction is completed, and then its inauguration is, so in the offing. Cavity formation is a very often, so that happens. So for that, so what we do is, so that because cavity formation means this is the face, you are drilling, so this side, so this is going to collapse. So when it is collapsing it, so that you cannot actually go forward. So you try to pack it up, so with the gunny bags, so this, and shortcut it, the face. So you are creating a wall type, and then, so then you are putting it, so these pipelines, so to grout it, so that you are stabilizing it, so the area behind, and then once it is actually stable, so then you can, so do the tunneling, so the forward. So this is another tunnel, so the similar type of, so the scenarios. So this is the Jozilla Tunnel. So this is a very another interesting, so the problem. So the tunnel is, so the very closer to the slope. So when you have a tunnel very closer to the slope, the either side, so the stress distribution are different, and because of this, so because of this, so you will be getting a chimney formation. So once the chimney formation is actually happening, so then there is no way, so that you can so control the issues. So the project is finally completed, so by the mitigation measures, so which have been, so they indicated. And similarly, the swelling is a very common problem. So because you do have the shales, so the shales primarily, so the consisting of, so the montmorillonite and the illite smectite, so the clay minerals. So in the invert, so you will be getting the water. So from the invert, so you will be so these are the mitigation measures. So yeah, you can see some of the slides, so your face is actually collapsing it. So controlling, say such scenario is an issue. The portal stability is, so the very important, say for Sangal Dam, the very treacherous, so So I will be completing it in another 10 minutes. So what are the time that has been actually given? So hopefully, so that I will be able to do it. Nothing to worry. So the portals are very important. So if the entry is actually the closed, so then you are trapped, so in the tunnels. And recently we have been, so the okay. So no issue. So in this, so we did, and then so initially we had the collapse, and the collapse is actually under the control of so the Bernard, so the very international companies. So and subsequently, so this was actually put to proper shape. And this case, so the very classical case, Subansiri, 2000 megawatt, so the powerhouse. And this, so after the construction, and the 160 meters, so the height slope is all done. But then, so it collapsed. So this was, so the recasted, and then, so the redesigned, reconstructed. So the project is actually the waiting, because the waiting is actually because of some other reasons, but otherwise, so it is. Similarly, the Parvati 2 project is also stabilized, so it is also, so the waiting. Important thing is, so the blast and impact. So when we say that, so the future is underground, I keep always telling to my students, so the future is underground, because we will be constructing it and doing, so the all variety of projects, so underground. What if, so if they are attacked? So there are, so the missiles which can actually penetrate. If you see it, so the Indian the terrorist attack, so the scenarios, so there is terrible, so they hear. So enjoy the pictures. So this type of things, so that can happen. So in a city environment where the tunnels are actually less than, so the 10 to 15 meters, so the depth. So the collateral damages, so they will be high. But so the being in academic area, so I won't be able to do the blast, so the studies. But the blast studies, so they can be conducted, so through the numerical modeling. But however, so to get the vetting of these numerical methods, so you need a direct, so the measurements, scale down, so the modeling. So that you can do it, say through the impact mission. So that's the reason why, so we designed, so the impact mission. So that is the models, tunnel models, lined, unlined, in different variety of, so the materials. And this is for the initial, so the characterization. And then subsequently, so you make these models. So these models, so they will be subjected, so to the loading. So that is the mission, so that has been actually designed. So because after all, so the impact is, so the energy. So even in the blast also, so the energy. So both can be equatable. So these are when the impact is actually happening, so how do you get the deformations of, so the tunnel. So that's, so they attempted, so they here. So these are the different profiles which you will be getting it, so with the different energies, etc. And then, so we could, so make through the prototype a relation, so between so the impact, and then as well as, so the blast. So thereby the blast loads, so there can be the damages of the tunnels under the blast loads, so they can be comprehend. Okay, so sorry. The future research is, so the going on, so the interacting tunnels, so the twin tunnels, intersections, so they're varying from 0 degrees to 90 degrees. So these studies are actually underway presently. The last one, so the seismic. So people said that, so the underground structures, so the no issue for the earthquake, but so we are doing it, so the high earthquake magnitude, so the regions, so the Himalayas. So thereby issues are there, so they across the Chichi earthquake and other earthquakes, say from the Japan. So it is very clear that portals are important. So if that is actually the so they're given up, so then issue. Then inside also your lining is the backbone, so for the tunnel. If the lining is, so the disturbed, so the tunnel is, say as good as, so the useless. So what I mean to say is, so the under the severe earthquake, so the conditions, issues are there. So that we have initiated 2000 onwards, so the seismic microresonation of different areas of India, and the basic seismic microresonation maps, so we are using it, so for predicting the ESBRL tunnel projects. So what if, so the when you have a high magnitude earthquake strikes, so these tunnels, different tunnels, can we, so create visualize, a damage scenario for the futuristic, point of view. So that's what actually the presently we are working, so the very hard on it, and then, so we wanted to create a system by which you will be able to know what type of, so the damages could be possible, so the in a given a earthquake condition. So that the fragility curves, so which we are developing it, so the based on the seismic, so the so we are developing that particular model. So luckily, to save the time, so I have not actually made any conclusions here, because the conclusions are very clear and obvious. I don't want to reinstate, so the again, say that. The conclusion is actually this, I take it, because since it is a occasion for to remember the Terzaghi's contributions, so I think that, say this is very apt in the sense soil or the rock, so different, so that is reflecting, so in all our projects, so in all these tunnel projects. So, but this is in 1946 or around that. But then you see the greatness of this man. What he said? He said that, so this is 1452 to, so 1592, so the great man, so the Leonardo da Vinci. So he says that I have been discovered methods of tunnels and engulfed secret ways which are excavated without any noise in order to reach predetermined locations, even if they have to be dug under the ditches or the rivers. What a man, so the 500 years back, so or more than the 700 years back, so he predicted that I know how to do the tunneling, so without any noise, and, so whichever direction, under any type of, so the terrain, so that I can do it. We don't know, like, so what is in his mind. So I take it as maybe this is the futuristic, so the view we should actually take it, and then that is how actually I read it. Thank you very much. So I have, so the IGS. Thank you for giving this honor, and also, so the Mumbai chapter. So you did a great work, so in organizing this, and then, so I have, so my teachers, so Professor Madhav, Professor, so many are there, so in my, so the elaborate Thanksgiving, I have written the names. So the mentors, the seniors, and the colleagues, so the funding agencies, and also the HICO, which is always, so that design my equipments, and my family and my extended family of, so the students. That is, so the very large, and the doctors of Siliguri who operated on me, because of that, I am standing today here. So the 10 days back, so I had a serious, so the bone injuries, and then they put me together. Probably, if you are not knowing it, so that I am having this. So thereby, so it is very apt, so that to thank, so my doctors. So thank you for your attention.
Thank you, Professor Rao, for the nice and very informative lecture on tunneling, the rather art of tunneling. And lot of tunnels are being excavated in Himalayan region for different purposes, like from hydroelectric projects up to the for the transportation. So most of the work will be beneficial to all of us, those who are attending this particular oration. So thank you so much. So on behalf of IGS, we would like to present a memento and the citation to you. And thank you so much for giving time for this particular oration. In spite of your, as you said, I know that the accident happened in Sikkim. So thank you so much for coming over here.
Thank you, Professor Samadhi and Professor Shahu, for chairing and co-chairing the session. We'd like to felicitate Professor Samadhi. So we had two excellent presentations today. With this, on behalf of IGS Mumbai chapter, I'd like to close this. Before that, let me just thank you for staying for the afternoon. Right?
On behalf of Indian Geotechnical Society, I thank Mumbai chapter for organizing the Terzaghi Oration lecture. It was very nicely done, and my special thanks to the student volunteer who supported this event. I also thank our both speakers, Terzaghi Oration speaker, for coming all the way in spite of their adverse conditions, and Professor Brad came from 7 seas apart, and Professor Rao, in spite of his accident, could make it. So I thank them from the bottom of my heart. Thank you.
It's okay. There is some high tea arranged on the first floor for you. Thank you very much. Okay. Thank you.